The solar system without planet 9 is 5 sigma ruled out. And the solar system with planet 9 is indistinguishable from the data. It's surprising that the most unstable, boring part of the Kuiper Belt gives you the most statistically significant thread. That's the most stringent evidence we have that planet 9 is really out there.
The quest to uncover planet 9. New research that will be coming up involving LSST, or the Rubin Observatory in Chile, where the next frontier in planetary research, not just in exoplanets, as we've talked about way more than this topic. This is inner planets, planets in our own solar system, beyond the orbit of Neptune. And last but not least, you're going to hear a deep dive into the physics behind Jupiter's past history. How can we do archaeology on planets in our own solar system? Well, Konstantin's figured out a way to do that. And it involves, of all things, its magnetic field. You'll hear about that, see the latest research into the planetary dynamics of our own solar system. Konstantin's no stranger to attention. You'll see him featured in 60 Minutes. Now, I want you to sit back, relax, and enjoy this episode of Into the Impossible with the irrepressible Professor Konstantin Batygin. Welcome back, everybody, to an episode that promises to be out of this world with a friend, a two-time guest on the Into the Impossible podcast, Professor Konstantin Batygin. Welcome, my friend. You survived fires and floods and mudslide potential to be here.
What? Yeah, and then we're not even talking about the drink.
No, that was just to get down here.
Yeah,
I mean, that was wild. I always thought it was a good day to come down to San Diego. Whenever I'd leave Caltech's confines and come down here, I always felt it was a good day. We're so happy you're here. Going to be talking about
it's good to be here, man.
The Hebrew planet, as I call it, Jupiter. You know, Jupiter.
Yes.
We'll be talking about that. We'll learn about how it got its size. You collaborate with Fred Adams, I think, on that.
I sure do.
Recent paper. He's been a guest a long time ago. I got to get him back. And I'll use this as an opportunity to do that. But first, we got to talk about updates to the most important topic, your band. How's your band doing?
Man, my band is doing awesome. So we played a couple gigs, I think it was in November and December, and it's been a tremendous amount of fun. Like the club we play at most often now, the Mix, has this like huge screen behind the stage. And so, we've been kind of incorporating that into the show, and also just because like AI video production is now so easy.
So good.
It's been kind of adding an extra element. We're working on a new album, so things are going, knock on wood, things are going well.
That's awesome. Okay, let's get to some of the meat of the conversation, because we're going to talk about lots of things involving planets. I have some planetary swag. You'll find out about that in just a bit.
Good.
But the first thing is, for someone who's not familiar, Planet 9, we used to have Planet 9. Actually, this asteroid up here, you can barely see it. It's called Asteroid 6618, Jim Simons. Got that named after Jim Simons. Mm-hmm. And it was discovered by, see the discoverer? Can you read that?
Clyde Tombaugh.
Yeah. Now, what's the importance of Clyde Tombaugh in the world of planetary discoveries?
Well, Clyde Tombaugh famously discovered Pluto. Of course, right? Pluto was the original Planet X, right? If you go back in history about a century ago, right, there was all of this discussion about there being an additional planet, which was largely driven by Lowell, right? And like Lowell Observatory was in part constructed in order to look for this elusive, planet. And Lowell died, I think, in 1916, but the search kept going, and Clyde Tombaugh, who was employed at Lowell Observatory in 1930, discovers Pluto. Now, one of the things that I think many people don't realize, when you just discover something up in the night sky, you don't know how massive it is. And so you kind of say, well, I was looking for a thing that was supposed to be 7 Earth masses, so it's probably 7 Earth masses. But Clyde Tombaugh immediately realized that, well, if it was something that big, you should be able to resolve the disk. And instead, it looked kind of like a point source. So he was like, probably 1 Earth mass? Like, there's no way to calculate it if it doesn't have a satellite. And, you can watch Pluto's mass kind of decrease through the literature. And there's even some joke paper from like the 80s that makes a plot of Pluto's mass as a function of time between 1930 and like 1980 something, and predicts how Pluto would disappear, right? It would cross zero in like 2005 or something like that.
Antimatter.
Yeah. And so, it was really realized only in the 70s when Charon, the satellite of Pluto, was discovered just how minuscule the mass of Pluto is. Yeah. And so that was the kind of story that led to the demotion of Pluto. Mike, of course, my partner in crime, had a lot to do with that back 20 years ago. But the thing we're looking for now is not some minuscule thing, right? The thing we're looking for is the legitimate Planet 9.
Mm-hmm. And it would be far beyond the orbit of even Pluto, correct?
Oh, yeah. About, about factor of 10, 15 further away.
Wow. Yeah. Nowadays, we don't use, pencil and paper like Lowell or even Leverrier did, right? No. I recently discussed with Davis Sobel, who wrote a lot of wonderful books, including a book called Galileo's Daughter. She talks about that. Mm-hmm. And we were just musing on how many, amazing discoveries Galileo made, but he also discovered Neptune. He didn't realize he discovered it, but he discovered it. So I aspire to be like that. I aspire that my blunders, like Einstein's cosmological, should be as good as that. But nowadays we have n-body simulations and so forth. And to me, as a scientist, that opens up, a whole new realm, including AI, machine learning and stuff,
Absolutely.
But also potential pitfalls. And I wonder if you could respond, some of the critics say when you're talking about this object, which we call Planet 9, mm-hmm. and that you are at the very, very forefront of its investigation, that, there could be artifacts introduced because of these n-body simulations. So can you explain why it's so important to discover this, and what are the new tools and new pitfalls of those new tools?
Yeah. Okay. So first of all, the n-body simulation as a thing, right, is in effect a numerical experiment, right? It is a realization of the solar system as it unfolds over its lifetime. You start off with a reasonable initial condition, and you say, I've gotten to the point where we are now at 4.5 billion years after the formation of the sun. Does the solar system that I've created in my numerical experiment look like the one that we see? What are the pitfalls? Well, the pitfalls, the simplest one is just in the method, right? You can, if you're not careful, you can screw up, and you can introduce like fictitious dynamics into your simulations. That's pretty easy to get. Like at this point, that's almost never a question, right? Mm-hmm. I think much of the discussion, right, has been, related to Planet 9 has been, okay, you do this numerical experiment. How do you then compare the output, like what we see at the end, to what you really see on the night sky? And this is where I think my collaboration with Mike has been the thing that has, for a change, made us greater than the sum of the parts, not less than the sum of the parts. Because, Mike is an observational astronomer. He's a ninja when it comes to understanding, right, what the night sky is telling us. And we've been, I think, through the kind of back and forth, which sometimes gets kind of loud, but it's all fun. We've been able to kind of challenge each other and really get down to the question of how do we take this output and compare it meaningfully with what we see on the night sky? Because, of course, when you're observing stuff, you don't just have access to the entire solar system. You just have access to what you can see. Right. That leads to a well-defined number, which is the false alarm probability of this entire story. And there are different lines of evidence for Planet 9, and like the two that I think people like to talk about because they're kind of the easiest to imagine is that if you go far enough away, all the orbits are all facing, they're all kind of like swinging out in the same direction. Mm-hmm. And that has a well-defined false alarm probability of about 0.2%, right? There are other lines of evidence like that are somewhat higher, like 5 sigma one. So you can do all this in a pretty rigorous way. Mm-hmm. But the point, I think, is that you can't just do a simulation and say, well, here's what I got,
So when Galileo turned his telescope, here he is there, not this actual guy, but he turned his telescope to the skies in 1609. He looked at the moon. He saw it was flawed, full of craters, mountains. He measured the height of the mountains. The guy's incredible. And and speaking of the moon, this is actually you get to choose which one of these do you think is more valuable? Actually,
well, definitely the smaller one.
The smaller one. Yeah, this is from your former home country. You don't get this one. I'm keeping this one, but you'll probably like this one better. This is a piece piece of the moon. Okay. So this was delivered not by the NASA astronaut. This is Chelyabinsk meteorite from your former...
Chelyabinsk.
Yeah,
say again. Chelyabinsk.
Chelyabinsk. Spasiba. This is a piece of the moon. Okay. And the reason I'm giving that to you is I'm so grateful that you're here for your second appearance, and that is real. And you'll get also a piece of the proto-solar system. This is a meteorite. So this is a chunk of...
this is an iron meteorite.
Yeah, this is from the Campo de Cielo in Argentina, which you will win too, guaranteed, if you're out there and you have a .edu email address and you live in the United States, briankeating.com/edu, or you can take your chances if you don't have one, unlike Konstantin and me, at briankeating.com/list, and you can join up there. But the reason I give this to you is because when Galileo discovered these four little stars, he called them after his funding agency, not the NSF, but the Cosimo Medici family. He called them after them. Now we call them the Galilean. What I'm getting at is that then, added 4 new moons to the retinue of moons that we knew about in the solar system alone. To what extent, if we found planet 9, would that essentially imply planet 10, planet 11, planet 12? Would there be many, many more to come, essentially?
Yeah, so the solar system has quite a bit of real estate, right? You can keep moving out. Eventually, though, you run out of real estate that's stable, because eventually you start to see the galactic tide, right? And the galactic tide, functionally basically just takes your orbital inclination with respect to the plane of the galaxy and trades that for eccentricity through something akin to what's called the Kozai effect. And in any case, there is sort of half of an order of magnitude left still in semi-major axis, but once you go well beyond that, passing stars, the galactic tides start to really mess you up. That's why, kind of where Planet 9 is, or where we infer it to be, is in the region we call the inner Oort cloud, right? Where it's material that could have been trapped there by interacting with the solar system's birth environment, like the cluster of stars in which the sun formed. Now that that's gone, there isn't really a way to trap material there anymore. And well beyond that, you're in the Oort cloud, and the fact that we have Oort cloud comets, right, that come in is just a manifestation of the fact that if you're in the Oort cloud, you're not just sitting there forever orbiting, happily. There are dynamics that unfold.
It will cause you to be much more elliptical and then eccentric and then eventually trans out of the Kuiper Belt, right?
So I'm not saying,
into the
Kuiper Belt.
It's
impossible.
Right. No,
I'm saying it's into the impossible.
And you talk about this thing, which I think is very interesting, at least the names of it. I love these names that you give. The Perihelion distribution dynamics. You talk about this Planet 9 inclusive model being relatively flat. This is some distribution function in your most recent paper that the graduate students will be quizzed on later on today after your wonderful talk.
Yeah.
Talk about that. What is a flat distribution to me? I mean, wow, there's got to be many of these things, and yet I can understand because of the clarity of your presentation just now that actually may not be the case, that there's sort of an infinite number of planets left to come. I mean, planets that we would say are honest to goodness planets, not chunks of Pluto or asteroids.
Yeah. So the most recent paper is something that we were inspired to do, and this is work that I did with Mike, but also with my close collaborators, Sandro Morbidelli at Nice, and also David Nisworny at Boulder, at the Southwest Research Institute. So for about 8 years or whatever, however long it's been, I guess now 9 years, that we've been working on this Planet 9 shtick. We have always been focusing on the most distant, the most kind of untouched orbits possible, because Neptune messes stuff up. There's a subset of the Kuiper Belt which we kind of ignore because we say, well, at close approach, it hugs the orbit of Neptune, and the chaotic dynamics that ensue from interacting with Neptune make that.
And just to set the stage for the listener who might not be familiar, the solar system goes out to Neptune, the classic planets, then the Kuiper Belt, then the Oort cloud, then the heliopause or something.
Then the end.
Whatever.
Yeah. Right.
Okay. So you were saying Neptune tugs on it.
Right. So stuff that is kind of in the outer solar system, whose evolution is chaotic, and stuff that's out, is kind of being thrown out of the solar system as we speak. So we kind of tend to ignore that and only focus on the orbits that are sufficiently detached, sufficiently calm, that we know that kind of a gravitational footprint of Planet 9 has a chance of being seen in these orbits. And so what we thought about a couple of years ago, I guess a year and a half ago now, was we're like, well, let's now look at the opposite extreme. Let's now look at the most unstable component of the Kuiper Belt. And these are things that orbit in the plane of the solar system that physically cross the orbit of Neptune. And so they're being actively scattered around. Now, if you reason through a question of like, should such objects exist in the first place? The answer is basically no, because their lifetime in the solar system is 10, maybe 100 million years at most. So the Neptune should clear the solar system out. Right. But if Planet 9 is there, then Planet 9 should be systematically injecting these things back into the solar system interior to Neptune.
And it would have to clear out its orbit, right, to be consistent with our friends at the only union I'm a member of, the International Astronomical Union.
Yeah.
Right?
And so what we did, so we did is we conducted numerical simulations, which I think are the most kind of encompassing n-body simulations of the solar system of evolution that, have been done, perhaps. And, we asked the question of looking at this highly unstable component of the Kuiper Belt, right? Can we rule in a solar system without Planet 9? And what we found is that the solar system without Planet 9 is 5 sigma ruled out. And the solar system with Planet 9 is indistinguishable from the data. So that, even though it's kind of a surprising, it's surprising that the most unstable, kind of boring part of the Kuiper Belt gives you the most statistically significant thread. That's the most stringent evidence we have that Planet 9 is really out there.
So that's when we hear things like, the 5 sigma confidence, that's saying that ruling out the null hypothesis that Planet 9 does not exist. Right. Very good, very good. Yeah. Now, how much of this depends on data? When Leverrier predicted the existence of Neptune, and then it was found the same day or something like that, the legend goes, or very soon after. And then, of course, he went on to blunder and predict Vulcan, right? So, sometimes if you only have a hammer, you hit yourself in the head too many times. Why is it so hard? I mean, no offense, but, if you told me I have to look in this area of the sky to see the CMB's B mode polarization, I'd be out there tomorrow with the Science Observatory, we'd be looking for it, right? So why is it so hard? If you know exactly, or if you're so confident that it exists, 5 sigma is the level of evidence for the Higgs boson to be awarded a Nobel Prize. So why is it so hard?
Yeah, well, I'm glad you bring up the Leverrier discovery of Neptune as a kind of counterpart, because what Leverrier was able to calculate very precisely was the acceleration is coming from there. Okay, and this had to do with the fact that he was doing the calculation in 1846, and Uranus and Neptune happened to be close to conjunction, and so the information that was stored in the Uranian residuals was actually not the mass of Neptune, not the orbit, but like where is it on the night sky? We're in precisely the opposite regime. What we can calculate from the orbits, like the orbital distribution of the Kuiper Belt, is the orbit and the mass of Planet 9. We don't know the phase. And so, you can draw orbits on the night sky all day long, all night long, right? And you can say, well, that leaves a lot of sky there to be searched. But I'm optimistic because the LSST is coming online this summer, and that's going to be a game changer.
It's always seemed to me can be surprising that it would be so controversial. Is it because there's so much pride associated with discovering a planet, because there's so few of them, that is so hotly debated? They say about academics like us, the stakes are so, the stakes are so low that we have these incredibly passionate battles. But here the stakes are high. Is that because of the pride? Is it ego? Is it swag? What is it?
I sometimes think about it this way. Like if I was sitting at home, whatever, drinking wine, reading the archive, and I read, I saw a posting that some rando is like, I'm thinking there's a planet beyond Neptune. I'd be like, okay, moving on.
Yeah,
right? Like, there's a natural skepticism that you kind of gravitate to. And, I think another component to this is that planets beyond Neptune have been predicted by everyone and their brother between 1846 and now. And it's always been wrong. Like there was this one guy, Pickering, who predicted I don't know, like 30 of them.
He was at Harvard, though, right?
We can't consider that guy. I think there's a Bayesian prior, if you will, to this story being wrong. But I think it's important to simply follow the data, right? And just say, okay, what is the data telling us, right? Meaningfully, like, we know that the data is biased, right? Let's account for that. Like, does it look promising? And sometimes when, as you say, the stakes are high, when the problem is important, I think it's important to take a bit of a leap. And even if your initial kind of significance is only, 2 sigma, right? Something that where you not something to write home about. Like, I think it's important to pursue those things, because the worst thing that's going to happen is you're going to be wrong. And like, no one's going to die, right? It's going to be okay.
So I have to always interject whenever my guests, like Konstantin just did, or I've had 5 Nobel laureates sit right where you are. Whenever they make a point that's really crucial to the development of good scientific habits, I like to double click on that and really enforce that for half my audience is young people in academia, not half, but more of my audience has PhDs than only has high school degrees, and these are people that are easily going to be influenced for good or bad. And so when Konstantin said just now that the stakes aren't life or death, like you just survived a fire. At the same time, the stakes for kind of what makes us, enriched as a species is the exploration. And so what you're doing has to be balanced, that tempered, notion of not only accepting what you want to be true, because it would be great, but also to realize, yes, it's important, but there are other things that are important too. So I wanted to highlight that. One question I've had as a lay person in this field, I mean, I love looking at planets and whatever planets and the moon got me into astronomy, and but now what I do is so far away from it.
Well, the night is young.
What's that? Yeah, I know. I could become your graduate student. That's what I'm thinking. I'm going to return to Caltech to be a student. No, one of my kids wants to go there. Maybe he'll end up with you. But tell me, Konstantin, the 3-body problem. It's seemingly the most complicated thing in the world. Like, how can you predict with how many things could be? There could be 1 trillion objects in the Kuiper Belt in the Orbital. How can you possibly predict anything? I mean, it's remarkable that you even have, forget about the phase that's unknown currently, but that you have this 5 sigma confidence bound on something that is a localized probability cloud, however you want to describe it. How is that even possible when the 3-body problem says you can't even do that with 3 bodies, let alone trillions?
Just because something is chaotic does not mean it cannot be understood, right? I mean, think about weather. Okay, weather is chaotic, right? And the lap of time is whatever, a couple days, right? So the time for weather to forget about its own initial conditions. And just because that's true doesn't mean the weather forecast is going to be horribly wrong, right? And so similarly, when we're dealing with the outer solar system, the dynamics instilled upon the Kuiper Belt, right, kind of tells you what's going on, not because each particular orbit is super important. Like, you should never obsess over one particular KBO. It's their cumulative statistical nature that points to what's going on. So each one is kind of doing its own, stochastic thing, but cumulatively there's emergent, right? There's patterns, right? Similar with like the stock market, right? Each stock might be quite stochastic. The cumulative behavior actually embeds some information about what's going on.
It's the difference between a complex system and a complicated system. I would say, like, building a 787 is really complicated, but if you do it with the right parts, the same time, every time, you'll get the same results. Not so with a sand pile or with, the weather in San Diego or Pasadena. But that doesn't stop people, right? So in my field, when we come up with an anomaly, which is very exciting, and it should herald, joy on the part of scientists, not like depression, I was wrong. No, I always say when you encounter a flaw, it could be a new law, right? So in the context of what I do in cosmology, we have something that's unknown, like dark matter, okay? So there'll be millions of alternative conjectures, whether it's a different particle, it's a field, or in fact, it could be a new modification to Newtonian dynamics.
Sure.
Does that come into play? Are there those? I'm sure there are those, but where do you rank these in terms of Mond equivalents for planetary science, and in particular things that aren't as abstract, like they call them rogue planets, other trans-Neptunian objects? How do you rank the alternative explanations? Put up the straw man and then burn it down for the
Okay. No, I mean, this is an easy exercise to do, because when an alternative explanation comes out, right, I try to not just believe it, but I try to go through and simulate it better. Okay, an example is there have been an example, actually, Mond. This is not my simulation, but David Nisworny, who, as I mentioned, is my collaborator.
Yeah.
When Mond was proposed as a replacement for Planet 9 to create all of these structures in the outer solar system. And of course, because Mond has this tunable parameter of where you transition from the
right.
Newtonian to the non-Newtonian regime, right? There were a couple papers that pointed towards this, and this got tested with very, very high fidelity numerical simulations, and these simulations showed that if that was the explanation, then the Oort spike of comets, which we see very well, would just go away. So it's ruled out. Could it be self-gravity of the Kuiper Belt? This has been an idea that kind of floated around. We looked into this and dedicated a lot of GPU time to actually studying this and convinced ourselves, no, and this is all published, like this cannot work actually because of Neptune scattering, etc. So each of these alternative explanations are interesting, and I've been interested in them, and I've dedicated time to kind of studying them. And I think it's really important not to be religious about your own, your own
confirmation
ideas.
Bias is a hell of a drug.
It's a hell of a drug, yeah. And so, that's what we've been doing so far. There is no theoretical, alternative model that I think is able to explain the data nearly as well as the Planet 9 hypothesis.
Hey, if you're enjoying this, I hope that you'll also subscribe to my Monday Magic mailing list, where you'll get to hear some behind the scenes info about this interview that I did with Konstantin and many, many more subjects that I like to share with you around the universe, the multiverse of minds that I get exposed to. And I love to take you for a ride. Once you subscribe, it's free. And if you have a .edu email address, you're guaranteed to win one of these beauties, a meteorite, a fragment of the solar system, before Jupiter, before Planet 9, before they were all even glimmers in the cosmic eye. So please subscribe. If you don't have a .edu email address, that's okay. You are entered to win automatically a competition. Each month I give away several of these to people that aren't blessed to live with .edu email addresses. But for now, let's get back to the episode. You mentioned you dead named, the Vera. No. You mentioned LSST. Talk about that. What is the excitement all about there? What are you gonna? I've heard everything from Avi Loeb, who's been a many-time guest on the show, talking about how they're going to discover an Oumuamua every night. Are you going to discover a TNO or a Planet 9 every other? How is it going to revolutionize what you do and what Mike does? And your collaboration is a rich one.
Right. Well, look, fundamentally, finding TNOs is conceptually not that hard. You take a picture of the night sky, and then the next day you also take a picture of the night sky and you look for what has moved. And the third day you do that again and you say, did that move in a consistent manner with this being a TNO? Boom, I've just found one. Okay. And for the first year or so, all you know is how far away it is and where it is on the night sky. You have some constraint and inclination, but you don't really have a good handle on the orbit first. So you need this string of 3 consecutive observations to tie together the exactly. And LSST is going to do that very, very efficiently because its entire job is to wake up every night and kind of look up and down the sky, record what it saw. So it's going to do a lot of things for many different fields, but I think for the outer solar system, in a way, it's a really good survey. It might not go deep enough, and it might not go north enough to find Planet 9 directly. But even if it doesn't, it will still provide an independent check on all of the predictions that Planet 9
Okay, so think big. 60 Minutes calls you up again. They got a bag of cash. What's the Batygin Observatory look like? If you could build whatever you want, money's not an object. Where would it be? What would it look like? Design it for me in real time.
It's just like my laptop in my office and the door closed. Okay.
And an infinite supply of the impossible coffee, right?
Yeah. I think instruments. Right, you don't need to really dream here. Right, instruments like Subaru, like the Japanese National Observatory, and the
Mauna Kea,
Mauna Kea, they're out there. But the thing that has prevented us from conducting a search that's really nailing down the northern hemisphere is really the efficiency. It's the fact that you only get a few nights per year. And you're dominated by the worst night that you have of the sequence.
Night,
And I wasn't an observer, and I'm still not an observer. And I'm happy about that. But
keep you out of my lab.
But I do now, having started this, observing about a decade ago. I now have this deep appreciation and gratitude for each data point that comes up, because especially for all the Planet 9 stuff, that stuff is up in December, like January, a little November sky. And the weather in the northern hemisphere is actually not that good. And so that's like something I learned is that it's actually not that good. You're like, they're fogged out, there's snow, the seeing is crap. So it's really tough. It's really tough. It's not as much fun as theory, because with theory, as you know very well, right, you're creating the world from scratch, so to speak, from axioms. It's so much. There's so much joy in doing that.
And instant gratification.
Yeah. With observations, you're just kind of at the mercy of the telescope, the conditions, and also what exists in the solar system.
Yeah, that's right. We're taking a little break from the in-person episode. I need to fold in the actual lecture that Konstantin gave. He gave me permission to share the lecture on Planet 9, and you'll see later Jupiter's magnetic field. This is a deep dive. It's a little technical, but it's captivated the imagination. So watch this deep dive where he's going to take us through what I call an office hour, an actual presentation by a top scientist, perhaps the top scientist in this field. And he's going to walk us through the evidence that we have for Planet 9. It's fascinating. I don't want you to miss it. And I'm so grateful that Konstantin gave us permission to share this little nugget of wisdom. Then we'll come back to the follow-up of that in-person interview where I discuss the fascinating aspects of how we know what Jupiter's mass and size were some 4 billion years ago. So stay tuned for that. Now into Planet 9, and stay tuned.
This is the solar system, okay? This blue thing here is the orbit of Neptune. Back about a decade ago, me and my friend Mike, inspired by work that some of our colleagues, Chad Trujillo and Scott Shepard did, noticed that if you look at the most distant orbits in the solar system, they all swing out into sort of the same direction, and they all are inclined with respect to the ecliptic plane by about 20 degrees. And we thought this was kind of a big deal. Well, now, the data set has evolved over the decade. It's sort of expanded by about a factor of 3. This is from a paper I wrote with my friend Morby in 2017. Then you can sort of see in 2019, there's a little bit more objects. In 2021, more objects still. And that's more or less what the data set looks like right now. Okay. So looking at this, I think you can just like kind of tell there are more orbits swinging out this way than another way. And so why is that? Well, can we invoke that something bad happened to the solar system when it was forming? Maybe a star flew by and kind of aligned all of these objects and we're seeing this relic. The answer is no. Because if you leave the solar system alone, all of these objects will differentially precess, and that differential precession time, right, the time scale over which the structure would become fully axisymmetric, is a few 100 million years. Okay, so no. Moreover, you see a strong correlation with orbital stability in this plot. Objects that are very strongly interacting with Neptune, and in fact, Neptune is in the process of kicking them out of the solar system altogether, here as shown in green. Objects that are dynamically stable, whose perihelia are well enough removed from the orbit of Neptune that nothing happens to them, are shown in purple. And again, without being an awesome statistician, you can see by eye that the purple orbits cluster together much better than the green ones, which basically don't cluster at all. There is a much more sophisticated way to measure orbital diffusion. That's work that Gabriele Picheri, who's a postdoc in my group, just submitted, but maybe I will not spend too much time on this in interest of time. Okay, so if you believe what you see, and you see these orbits, and you're like, wow, they really are clustered together. How can that be? Well, you need something exterior, something extrinsic to perturb them, to keep them confined, and it has to be eccentric to break axial symmetry. And the rest you can compute from these types of forward models that are just numerical n-body simulations. So what you're seeing here is an evolutionary model where you're starting off and for scale, this is about 30 AU, the orbit of Neptune. You're introducing a new planet on some highly eccentric orbit, and you're starting off with a rather axisymmetric disk of Kuiper Belt objects. And the blue orbits here represent long period things, right? Because, well, they have long period, and these golden orbits are things that are too short period to be strongly affected by Planet 9 induced dynamics. So it takes a couple billion years for a pattern to emerge, but right about now, we're starting to see how the anti-aligned direction with respect to the orbit of the introduced perturber is kind of starting to get preferred, right? There are more objects hanging out here. You guys also see this, right? Like, I'm not alone. Okay, that's good. Problem if I was the only one. Okay, why is this happening, right? Why anti-align? Well, as you can see, occasionally objects will process through orbital alignment. And when they process through orbital alignment, their eccentricity reaches a peak and their orbits get jammed into the orbit of Neptune, which then scatters them out of the solar system. Okay, so this is kind of a survival technique, if you will, of long period Kuiper Belt objects. Okay, and the same thing largely remains true also for the plane. Okay, so if we go into 3D, we'll find that the surviving objects also get tilted away from the plane, the ecliptic plane, by effectively bending of the Laplace plane, by gravity of Planet 9. Okay, there's also very high inclination dynamics that gets excited. Okay, good. So, if you believe that this is the case, right, then you can compute what the best kind of fit Planet 9 parameters are. And they turn out to be about 5 Earth masses with an orbital period of about 10 to 20,000 years. So think 500 AU in terms of semi-major axis, and an eccentricity of about 0.3, an inclination of about 20 degrees. That's kind of what you get from here. Now, there's been some discussion in the literature about whether or not this is actually real, right? People talk about, well, what if all of this is a conspiracy of observational biases that together make this pattern? And we've participated in that debate. I would argue that the false alarm probability here is 0.2%, but that's not what I want to talk about, okay? Because I want to leave that question for Vera Rubin. Instead, what I want to think about is a distinct process. Namely, up until now, right, I've been asking you to focus on these objects that are very, very stable, right? These things that are removed from the orbit of Neptune, so they're corralled by Planet 9's gravity. They hold the footprint or thumbprint of secular interactions with Planet 9. And also, if you were paying attention to the previous slide, you saw how we started out with lots and lots of objects, and then many of them disappeared, right? Because they got jammed into the orbit of Neptune. So what these calculations tell you is that if Planet 9 really exists, it should also, in addition to doing this confining business, drive a steady flux of long period objects that cross the orbit of Neptune. Okay. And, well, here are some numerical simulations of the chaotic evolution of the perihelion distances, for example, where you see that happening, where perihelia dip below Neptune, right? And then at the end of, as the solar system, at the moment when we're observing now, they're being just like jammed into the space in between the giant planets. All successful Planet 9s will do this, okay? Even the unsuccessful ones, okay? Every single Planet 9, unless it's like pathetic, and yeah, pathetic is probably like 0.7 Earth masses, okay? I'm making that up, but like that sounds right. So anyway, all successful Planet 9s will do this, okay? So we ran a couple simulations, and these are actually the most detailed simulations of solar system evolution ever, because they go through first the process of forming the Kuiper Belt, all self-consistently, right? The expansion of the giant planet orbits. They self-consistently capture the effects of the birth cluster in which the solar system was born, et cetera, et cetera. They include, perturbations from the galactic tide, passing stars. The only thing they don't have is like a simulation of me simulating, right? Like that's the level at which we decided we didn't want to see too deep into the matrix. Okay, so so we did 2 simulations because these are rather computationally heavy. One with and one without Planet 9. Okay, and here's the answer. Okay, this is at the end of the day, kind of as today's solar system. This is the distribution of perihelion distance, the closest approach distance of objects with semi-major axes presented on the x-axis. And what you see is that if you don't have Planet 9, then Neptune forms a barrier. Okay, in other words, as objects try to penetrate kind of interior to the orbit of Neptune, that process is so slow because the galactic tide is actually a painfully slow process that Neptune scatters them out before they can get well beyond 28 AU. If Planet 9 is there, on the other hand, it creates a rather flat distribution. Right? Populates all the way from 30 to 15. So what does the data look like? Well, the data for Neptune crossers looks like this, right? And I think you can look at this and say, yeah, these are not all sitting at 28 AU. But before you high-five yourself, okay, you have to be careful because there's, of course, a strong observational bias towards discovering things with smaller perihelia. So you have to account for that. The good news is it's very easy to account for that. Like we know that stuff becomes less bright as 1 over r to the 4th. We know how to account for the amount of time spent in a Keplerian orbit. It's a trivial calculation of the bias. So after accounting for the bias, what we find is that the P9 free solar system is ruled out at more than 5 sigma by the existing data set of Neptune crossers. And the Planet 9 inclusive solar system is at like 0.2 sigma away. So it's basically indistinguishable from the data. I am out of time, and so I will just leave with this image of optimism here as my last slide, because LSST, the Vera Rubin Observatory, is coming online this year, and all of this stuff, Planet 9 related, will be tested independently, and I think, we'll be well on our way either to proving all of this wrong, which would be kind of a bummer, but, that would be okay, or well on our way back to a full up, 9-planet, make the solar system great again level of planet membership.
So that was just awesome. Learning about the evidence for, or maybe against, the existence of Planet 9 from the world's foremost expert in it. I mean, how often do we get a treat like that? I needed to expose you to it because I want you to see how good science is done. And this is science at the cutting edge. You're hearing it first. These are brand new results from Konstantin. But even fresher results than on Planet 9 have to do with Planet 5, which is Jupiter. And Jupiter is the most important planet in our solar system by far, except for the Earth. I mean, I'm kind of partial to the Earth. But besides that, we might not even exist if it weren't for Jupiter having the properties that it has. And yet we don't know that much about it. There were no videotapes, no TikTok 4 billion years ago when it formed. How did it get to be the size it is now? Well, it turns out it went on a cosmic version of Ozempic, some kind of slimming down process to get to the size that it is now, 1 Jupiter radius. You'll find out why in this discussion we think that Jupiter was much more massive. Konstantin does, and his collaborators, including upcoming guest Mike Brown, author of How I Killed Pluto and Why It Had It Coming. He's also an upcoming guest, as I said. So now listen to this conversation with Konstantin describing how they know what they know about Jupiter's former size and mass. It's fascinating. Another cosmic detective story. I couldn't resist discussing this with Konstantin. And after that, we're going to go to the lecture where he describes it in great detail, and it's just a fascinating and once-in-a-lifetime kind of exposure for you out there, my brilliant audience, to get an insight into how astronomers really think and work. Okay, here we go. Let's move on to your topic of today's talk, which is on the formation of Jupiter and its the relationship between the magnetic field. This doesn't immediately strike me as, kind of in your research portfolio. Are you branching out? Are you moving out into, purely looking for, these Neptunian transits, Trans-Neptunian and Planet 9? Does this complement it in some way? Talk about the research. Why is it so important? Did Jupiter look different, and if so, how long ago could Galileo have seen a different Jupiter than we see to this day?
Well, so to answer your first question, I did my thesis on planetary interiors, actually, and magnetohydrodynamics. So orbital dynamics has always been an interest of mine, but I've always done that in parallel. And when it comes to Jupiter, the planet, in a way, is the most important planet of the solar system. No, I hope Planet 9 didn't hear this and didn't go into hiding. But Jupiter is the great architect of our solar system. There are things that would not
we wouldn't be here.
Yeah, we would be. Yeah, and so
Bodyguard.
It's critical to understand how Jupiter, the great architect of the solar system, arose. Right, and we have a pretty good, kind of theoretically, self-consistent, but nevertheless vague picture of first you form a core, then this core slowly accretes an atmosphere that's hydrostatic, and once the mass of the atmosphere becomes as big as the core itself, then you enter a runaway phase of accretion where the planet grows very fast to Jupiter mass. Mm-hmm. Okay, so when did that take place exactly? What was the state of Jupiter like, at some point after the sun's formation other than now?
Yeah.
We don't know. And so what this new work demonstrates is that there's actually a record of how Jupiter evolved about 4 million years after formation of the first solids in the solar system, that's embedded within the orbits of the tiny satellites that live inside of Io. Okay, so there's
satellites inside of Io?
Inside
the orbit of Io.
Yeah, inside the orbit of Io.
Oh, there are.
Yeah,
moons. Wow.
Everybody always forgets that these exist, but actually the first one, Amalthea, was discovered by Barnard.
Really?
Yeah, and
1826.
1890, maybe 90, but he must have had crazy good vision, right? Because this satellite is 80 kilometers across, and it orbits at only a couple, 2.5 or so Jovian radii. And there's another one called Thebe that's slightly further out. And as it turns out, the orbital inclinations of these moons store a record of where Io started out, how it migrated out tidally. And from this, you can infer a lot.
I have a little shameful detail, a secret, a metric to reveal to you, which is that only about a third of you that are watching, enjoying, or listening to this podcast or watching it on YouTube are actually subscribed and following me on those platforms. And it's quite a shame because we have so many cool episodes coming up with the actual man who killed Pluto, Mike Brown. It's coming up. You don't want to miss it. So please do subscribe or follow it wherever you're watching or listening to it. I guarantee it's worth your while. And if you wouldn't mind doing me a favor, an astronomical favor, you can't have your own constellation. Those are set. There's only 88 of those. But you could make your own asterism, a collection of 5 stars, hopefully, where you can review the podcast if you're listening on audio. So please do that on Apple or Spotify. It really means a lot to me, and it really does help us boost the visibility in the constellation of over 3 million podcasts. This is in the top 0.01% of all podcasts, but I think we're criminally undersubscribed. I hope you will do that and help me boost the ratings, visibility, and quality and caliber of the productions. I've really upped it. Better cameras, better sound, better lighting, and I know that you'll appreciate it. So please do that, and I hope you will see it will pay off. Of course, it's free, so it doesn't really cost you anything. Please do that. Now back to the episode.
The basic idea is that from Io's orbital record, right, you can also use, conservation laws, conservation of angular momentum, of the spin of Jupiter, etc., to read off what was it like when the gas just evaporated. And the answer is it was twice as big as it is now. Okay, wow. And it glowed at about 1200 Kelvin.
So it's almost brown dwarf, or even hotter than a brown dwarf, right?
Oh yeah, initially, yeah, absolutely. And so
was there fusion? Could it have fusion at that scale?
No,
because it didn't have as much.
Yeah. So the interior temperature, even DT fusion requires 70,000 Kelvin. It's at 50 at the so close, but no cigar.
But no fusion.
But once you know the interior state, then you can infer the magnetic field. Why? Because as it turns out, right? Rapidly spinning, spherical, fully convective astrophysical dynamos all fall in this regime of having a equipartition-like behavior where the kinetic energy of the convection is, so like rho v squared of convective motion within the planet is balanced by the magnetic energy density, b squared over 2 mu naught. And that comes from the fact that convection is the thing that's generating the field. Yes. And there's a bucket to put the energy in.
Right.
And so
unlike the solid rocky planets, right?
Right. Well, and so that gives you a couple hundred Gauss as the field of the primordial Jupiter. And once you know the radius and the field, and you know where Io was parked, you can actually also infer from that the accretion rate of gas that Jupiter was experiencing right before the gas went away. And that turns out to be a Jupiter mass per million years.
Holy cow.
So all of these things are actually not surprising numbers, but it is a model-independent way to infer them, and it's like stored in the orbits of these tiny
satellites. And are there
satellites.
implications for the survival? I'm just thinking right now about Earth, and as you said, Jupiter is the architect, but it's also like a bodyguard. Mm-hmm. We saw Shoemaker-Levy. You probably weren't even born, but I saw it in 1994 smash into Jupiter.
I was born.
Okay, fine. You're babyface Batygin, they call you. There's this notion of it as a bodyguard absorbing stuff. So if it was 8 times bigger, volume, it was 8 times more massive. Roughly, let's just, whatever. I'm a experimentalist, right? Does that mean it was even more efficient soaking up the meteorites, the meteors that would have impacted Earth, comets, trans-Newtonian objects, Planet 27? Could it have been more, of a bodyguard than it already was? And allowed life? I'm trying to get to, how life
I think certainly compared to the work it does now, like right now the load is low because there's not that much stuff coming in from the outer solar system. Okay? So just a flux of trans-Neptunian objects, becoming centaurs and being kicked around by the giant planets and then eventually reaching Jupiter to become Jupiter family comets. That flux is nothing compared to what it was immediately after the gas went away in the primordial solar system. Because when that happened, the solar system was encircled by 20 Earth masses of planetesimals.
Right.
And that stuff all had to get scattered out. So Jupiter was kind of working overtime for the in the first.
Will these Europa Clipper, JUICE, all these other missions, will they tell you anything? Are they more the outer moons, so they don't tell you as much about Io?
They will tell us a lot about the composition, the geophysics, and the geochemistry of the satellites. I work a little bit on satellite formation. I have a couple papers, and I'm really excited because that's going to kind of take the real constraints of just being there and kind of taking a look at what this looks like to the next level. For this problem, I don't think it will matter that much, but I always don't think things matter that much until they do. So
and then Leslie, whatever his name is, shows up on your doorstep. Her name is. Talk about the calculations that surprised me in this paper, the consequences of thermodynamics. I didn't initially see that there'd be any connection between the entropy, what you call the cold star and the hot star. What are they? First, explain how is entropy relevant to these calculations, and what bearing does the calculation from thermodynamics even have on a planetary system?
Okay, so can I tell a quick story that's like one of my favorite moments from undergrad? Is I had a professor in thermo who said on lecture 1, he's like, you have been all misled about entropy. You've been told that entropy is a measure of disorder in the universe or in your system, and that's just like forget that. Okay, in this class we're going to really learn what it is. But before you do, you have to first learn quantum statistics, then from it you're going to get to classical statistics. So there's like kind of 3 weeks of prep that you have to do before you really understand what entropy is. And then came the day when he was like, today you will learn what entropy really is, and it'll finally make full sense to you. Everyone's, super excited. He's like, okay, entropy is the Boltzmann constant times the log of the partition function. Do you understand? Right? So that's my answer. That's how it's all connected. It's the KB log of but to maybe bring it back to something a little bit more practical, right? Jupiter, by virtue of being a convective planet, is also very nearly isentropic. Okay. Even though temperature, of course, goes up as you go into the deep interior, if you were to grab a patch of gas from, halfway into Jupiter's radius and slowly move it back up to the surface, it would have the same temperature as the surface, right? Or as the radioconvective boundary, effectively speaking, right? And so the entropy is a much better number than temperature because it's the thing that defines the entire kind of curve of the interior profile.
It's a record of the trace of the path
exactly.
of history. Yes.
Exactly. And so quoting a number like whatever, 10.5, right, kb per baryon, right, that tells you how hot Jupiter is, not just at the surface, but how hot it is in the interior. It kind of gives you the full picture. Now, this hot start versus cold start problem is ultimately comes down to the problem of the shock. Okay, so when you're forming the planet, okay, and the planet is accreting and gas is falling on it, right? If you imagine, taking a balloon of gas and smacking it against another balloon of gas, if you do it slowly, it just absorbs, right? If you do it much faster than the speed of sound, it bounces. And so you get some energy release. So there's this question, which is this is a theoretically difficult question to answer, of how much energy is actually injected into Jupiter when it accretes mass, and how much of it just bounces off and radiates away. What this new paper suggests is that actually most of it gets injected into Jupiter. As you accrete, a large fraction of the luminosity that the planet exudes is coming from material that's being accreted.
So that was awesome. That was a kind of grand overview of what we know about Jupiter and how we know it. Now here's a deep dive from the slides from the presentation that we heard Konstantin just give to us here in person at UCSD. This is, again, a real and rare treat for you and me to experience the top performer in this field. It's like having Steph Curry, teach you how to do jump shots. So it's a masterclass from an expert, perhaps, again, the foremost expert in the world on the properties of our early solar system, including the second most important planet. Okay, fine, Jupiter. So now we're going to go into that slide, and then we'll come back to the very end of the interview, and then we'll have homework and takeaways for you.
So we've got all of these circles, right? These are all planets color-coded by the type of star that they orbit. And what I've done here is on the y-axis, I've done a slight variation. Usually people just to show the mass. I've normalized the mass by the mass of the central object so that I could also overplot the population of solar system satellites as these rectangles. So naively, just like without knowing anything, you can kind of tell that the population of giant planet satellites fits nicely with this cloud of subjovian extrasolar planets that, as it turns out, is the dominant outcome of planet formation in the galaxy. Now, there are many patterns that are being studied about this population today, and I would say one of the most striking things is that they're all kind of right here. Okay, no, this is a log scale, so it's easy to say right here and kind of cover a lot of space. But if you focus on this histogram here, it shows you a histogram of the shortest orbital period of a planet in a given system. And there's clearly some peak, right, that lives between a period of 1 day and 10 days. How do we understand this peak? Like, why should this be? Where does this come from? Well, in general, we think these planets, when they form, interact with the protoplanetary disk where they form, right? And they do so principally by raising wakes, okay, within the gas, and these wakes, gravitationally pull back on the planet. And so if you put a planet somewhere within the disk through this interaction, which is creatively called type 1 migration, there's also type 2. So through type 1 migration, the orbit just decays. And it decays all the way down to the place where the disk ends, right? And the disk, right, the protoplanetary disk, has a cavity because magnetospheres of stars tend to carve out this cavity. And this is sort of a well-known and well-appreciated feature of protoplanetary disks. Okay. Could it be a selection effect? Let's go back. It's easier to find stuff this way. Okay. So, no, it's easier to find stuff this way. So the fact that there's a drop off here is real. out here, is there selection effect? Absolutely. And people do very careful modeling of asking the question of like, is this fall off real? And the short answer is it's real. There's really a turnover in the knee of the occurrence distribution. Okay. So if you kind of accept that protoplanetary disks are truncated by magnetospheres, like people generally accept that to be true. And if you accept that this interaction leads you to decay to the inner disk, then you're presented with a bit of a puzzle. And this puzzle, I can highlight by going to three systems, which orbit three different types of stars. Kepler 256 has some planets. They orbit a star of a solar mass. And the innermost period is 1.5 days. And then if you go an order of magnitude down, the TRAPPIST-1 system, which is a very famous exoplanet system, in part because it's called TRAPPIST, and you ask, what is the innermost orbital period? It's also 1.5 days. And if you go another 2 orders of magnitude down and ask, where's Jupiter? Like, where's Io orbit? It's sort of also 1.5 days. So I don't want to make the impression that 1.5 days is, absolutely the critical number, but the order of magnitude is kind of conserved, even though the mass of the central body changes by orders of magnitude. So how can this be, right? How can there be within this context a deep state level of conspiracy where all disks get truncated at an orbital period of only a few days? So let's think about how this can be. Well, first of all, the physics of truncation of protoplanetary disks has been understood since at least 1979. Like literature in neutron stars by Gauss and Lamb was really the first to point out that you can compute this radius of the magnetospheric cavity by equating the magnetic pressure scale to the accretionary ram pressure scale. So you can do that, assuming a dipole field, magnetic pressure as usual is b squared over 2 mu naught. And for kind of spherical free fall, ram pressure, rho v squared, can be re-expressed in terms of the disk m dot. Okay. So these two things, where the radius at which these two things equal is where you cut the disk. Okay. So somehow, right, the radius changes with the central mass, right? But the frequency remains the same. So how can we have this? Well, let's construct a very simple model. So the simplest scaling that you can imagine for the accretion rate of protoplanetary or just like astrophysical disks is that the rate of accretion will scale with the mass of the central body. The data is actually quite fuzzy. This might be to the 1 power, this might be to the 2 power. Both are consistent with the available data, but for the simplicity, let's choose this linear relationship. Okay, so then we'll replace the m dot here with something that goes as m. Okay, what about the magnetic field? Well, for rapidly rotating, fully convective astrophysical dynamos, there exists an important scaling law that tells you that magnetic energy density, b squared over 2 mu naught, goes roughly as the kinetic energy density of convection, right? And then through mixing length theory, you can relate this in the usual way to the heat flux. Okay. There's a reason, by the way, I'm telling you all this. I'm not just randomly making stuff up. This is all going to connect back to Jupiter momentarily, but I'm having fun first with extrasolar planets. Okay. So this scaling law between the field strength and the luminosity of stars is a pretty well-established thing, and you can actually connect the geodynamo, the Jovian dynamo, M dwarfs all on the same curve. Now, what about the radius? Well, remember, early on, while things are encircled by disks, stars are contracting roughly as just Kelvin-Helmholtz contraction. And this is a well-known result that the radius then is also just expressed in terms of the heat flux. And as it turns out, if you put all of these things together, right, you can derive an equation for the frequency, orbital frequency at which the disk will be truncated. And all of the dependence on the mass goes away. Okay, and all of these various constants that appear in the scaling laws are there, but they come in at a sublinear power. Okay, so you kind of get this 2 pi over 3 days orbital frequency as a relatively universal outcome of disk truncation. And I would argue that the fact that Io and TRAPPIST-1 and all the usual Kepler exoplanets all orbit in a matter of a few days, it's just a reflection of the interplay of these mechanisms, right? Convective dynamo generation, just regular disk accretion, and Kelvin-Helmholtz contraction. So as we enter the age of characterization of circumplanetary disks, for which PDS-70C is the poster child, here's the poster, here's PDS-70C, there's clearly a circumplanetary disk here. If you don't see it, look again. Okay, it's there. Okay, this blob is a disk. Okay, so I would argue that as we, discover more of these things in the age of ALMA, we will find that these two will be truncated at a period of on the order of a few days. And that's the preamble. And the reason I wanted to tell you this is because much of the same physics that I just mentioned will come back momentarily when we talk about Jupiter. Okay, so why do we care about Jupiter? First of all, every person interested in celestial mechanics to have ever lived has concluded that the solar system is composed of the Sun, Jupiter, and other things. Okay. In fact, if you read the textbook of Arnold, not Arnold Schwarzenegger, but a different Arnold, like the mathematician, he kind of says this, and he says, okay, so everything else we'll do in this textbook is basically going to be in this framework of the restricted circular 3-body problem. Also, as our understanding of how the solar system came into existence has sharpened up, it's become clear that actually the formation of Jupiter played a great, defining role in setting the large-scale architecture of our solar system. Perhaps even the fact that the terrestrial planets are so low mass is connected to the fact that Jupiter formed. And these days, and by the way, Jupiter-like planets are not a given, right? Jupiter-like planets occur at around 10 to 15% of sun-like stars, much less common for lower metallicity, lower mass stars. So by virtue of having giant planets in the first place, our solar system kind of already scores at least a B+. Okay, so it's a pretty good planetary system. Yes?
Do you think when people said because we already know the biases for that, and we assume that they're just rare, or because we simply haven't found them around many stars?
15 to yeah.
Are we sure that these are not simply an observational bias?
Oh, yeah, good question. So is it simply an observational bias? I would say at this point, no, because some of the that number at this point comes from the California Legacy Survey, which has been going on for nearly 40 years, right? So, of course, with ever increasing precision, but at this point, in terms of period, we kind of go beyond Saturn. And there appears to be a drop-off in the occurrence rate before the bias really sets in. So there seems to be like a couple AU is the peak of where giant planets occur, and they're much more rare interior and exterior to that. So it's kind of this log Gaussian distribution. Okay, so today we know quite a bit about Jupiter itself. We've got the Juno mission, which orbits Jupiter, one of the goals of the Juno mission was to measure the gravitational harmonics out to degree like 12,000. It's not really 12,000, but it's some very, very high degree. I think they have like Legendre polynomial out to J14, right? So just crazy, crazy good understanding of the Jovian, the Jovian gravitational field. There's all this understanding of what's in the Jovian atmosphere. And I would argue that by comparison, our understanding of how Jupiter formed can be summarized in this plot from 1996. And this is still more or less the state of the art. So let's go through this plot. What is it showing us? Well, first of all, on the x-axis, it's showing us time in millions of years. Okay, and on the y-axis, it's showing us mass. So this plot can be separated out into 3 distinct phases, which are named phase 1, phase 2, and phase 3. Okay, phase 1, which is this phase, corresponds to the formation of the core of Jupiter. It's like from Jupiter gravity data, we know that there's about 25 Earth masses of heavy elements inside Jupiter. They're not concentrated in a straight up solid core. They're kind of distributed in a fuzzy core, but we know that the core is relatively deep seated. Okay. So once this core forms, then we have a protracted period of steady gas accretion where this core acquires a hydrostatic envelope, okay, that slowly grows in mass. Okay, it grows simply by cooling down. In fact, Eve has a paper about this, right? It's just like cools down. So when it cools down, it contracts a little bit, letting in more gas into the Hill sphere. That's the basic mechanism. And once the gas accretion allows the atmosphere to become as massive as the core itself, this process accelerates into a phase of runaway accretion, during which you grow up and graduate from sort of 20, 30 Earth masses all the way up to the 300 Earth masses that is Jupiter in a short amount of time. In fact, in these 1D models, the accretion rate goes as something like mass to the 4/3 power. And so you reach infinite mass in finite time. Okay. And the way that you explain that Jupiter is not infinitely massive is at some point you just have to turn off the code, right? Like when it goes through Jupiter mass, you're going to shut that sucker down. Okay. Shut off the gas. So this is from 1996. Okay. You're thinking, right? Nickelback hadn't even made it big. Okay. Like that's how old this plot is. Right? This is from 2019, and modern kind of 3D calculations more or less look like this, and they have had a illuminating effect in quantifying how the hydrodynamics of gas occurs when you have a young planet and that is embedded within a protoplanetary disk. And it's very, very interesting. But when it comes to answering the question of like, what happens to what's going on at the planetary scale, these models basically have no resolving power, in part because their softening length is about this big, okay, 0.1 Hill spheres. And it's frustrating because like I would like to know how Jupiter formed. Now, I'm not in the astronomy department at Caltech. I'm in planetary science, which is part of geological and planetary sciences. There are a lot of my colleagues are geologists. And one of the things that you learn about a geologist is like if you go out into a field with a geologist will kind of walk around for a while, pick up a rock, kind of look at it, put it back down, pick up another one to kind of smell it and be like, that mountain definitely formed 50 million years ago. Like I just know it. And it's like, how did you know? It's like, you just know. Okay. So I always kind of feel jealous that I can't just like look at a rock and just know how Jupiter formed, except for I think there is a chance. Okay. There is a chance. So Jupiter, and this is, by the way, a beautiful JWST image of Jupiter. So Io is, it's not in the image. It's further out. If you look at Jupiter close in, it's orbited by a series of rocks. And these are rocks that are maybe 80 kilometers across. And people always forget that these rocks exist. Okay, in fact, this one, Amalthea, was discovered by Barnard of the Barnard star fame. In his paper, he speculated about the kinds of aliens that live on Amalthea, which is pretty fun to read. But there's now, as it turns out, there's 4 of them. There's Amalthea here. There's Stebe, which is off the image, but you can see some of the light there. And there's a couple other really, really tiny rocks that actually create the Jovian rings. And these rocks, even though, by the looks of it, they orbit exactly in the plane, in the kind of equatorial plane of Jupiter, that correspondence is in fact not precisely exact. Okay. Amalthea is inclined with respect to the Jovian plane by 0.39 degrees, and Thebe is inclined with respect to the Jovian equatorial plane by 1.1 degrees. People in astronomy would like to say, well, what's 1.1 degrees among friends? That's like 0. But I would argue that these are, in fact, very, very meaningful numbers. Why are they meaningful numbers? They're meaningful numbers because they, in fact, hold the record of Io's tidal regression. Okay. Where do you see Io's footprint? Oh, this? Oh, okay. So Io is heavily volcanic, right? And so it's always the plasma torus is part of the plasma torus is accreting onto following the Jovian field lines. Okay. So given what I've told you in the first few slides about extrasolar planets, and the fact that almost certainly qualitatively the same thing unfolded in the Jovian system, namely the satellites formed somewhere by type 1 torques. They migrated and parked near the inner edge of the circumjovian disk. And that's actually why they're in a 4:2:1 resonance. Okay. So at the time when the disk is right about ready to dissipate, the picture is as follows. You have Io, Europa, Ganymede, Callisto somewhere here, and the 2 rocks, Amalthea and Thebe, are inside the magnetospheric cavity. Why are they inside the magnetospheric cavity? It's because, well, they're too massless to experience meaningful type 1 torques. They are just shepherded inwards by resonances with Io. I can dwell on that a little bit longer, but for now, just trust me, they were inside the inner edge. Okay. Now, then the disk photoevaporates at some point. Typical disks live for about 3 million years. I would argue that the solar system's disk lived a little bit longer. We'll again touch on this in a bit, but the disk photoevaporates. And then for the remainder of time, since disk evaporation, Io, Europa, and Ganymede have been slowly migrating out by tides raised on Jupiter. This is the same process as why the moon is receding, right? The moon is receding at about 1 centimeter per year. You have to enjoy it while it's there, okay? Because it's taken off, like it has had enough, okay? So the same thing is happening. And naively, we don't know, right, where Io started, right? Like we know that it's moving out right now. We can sort of do astrometry. But in fact, I would argue that by knowing the orbital inclinations of Amalthea and Thebe, you can very well constrain where Io started. Why? Because as Io, Europa, and Ganymede all move out in concert, they sweep a series of interior orbital resonances. Orbital resonances are configurations where the gravitational perturbations between these bodies become coherent. They correspond to integer period ratios. And as these resonances sweep, every time you cross one, you get a slight kick, both in the eccentricity and the inclination. Okay? The convergent encounters with resonances lead to capture. That's how Io, Europa, and Ganymede all locked into a 4:2:1 period ratio. Divergent encounters lead to kind of impulsive kicks. This has been understood since at least the 1980s, but probably even well before that. Okay, how does that work? When I was a grad student, first working on celestial mechanics, I was encountering these types of diagrams, and this looks like the Eye of Mordor, just like staring you deep into your soul. But then once you understand what's going on, it's super clear, okay? The keys to get there. So these are phase space coordinates, and you can think of the radius away from the origin as the orbital inclination of one of the tiny satellites, say Amalthea. Okay? As Io migrates, this homoclinic curve slowly contracts upon this equilibrium where you sit originally at 0 inclination. And because this process is adiabatic, phase space area occupied by your equilibrium is conserved until you encounter the separatrix. Now, the separatrix is an orbit of infinite period, so adiabaticity is briefly broken and you acquire some phase space area. And then as this process continues, this deforms back into a circle, and you have a very deterministic kick in orbital inclination that you can compute associated with each passage of each resonance. Okay. So in practice, what does this mean? This means that to explain Amalthea's inclination, you can calculate that it must have crossed the 3:1 orbital period ratio with Io. If you basically start Io too far away from Jupiter, then the inclination would be too small. But you can't start Io too close to Jupiter because then it would sweep too many resonances in. The inclination would be too high. The same argument applies to the inclination of Thebe. This is the one with the 1.1. To explain its inclination, you have to sweep the 6:4, 5:3, and 4:2 resonances across this satellite. So Amalthea offers a lower bound on where Io started out, namely 4.02 Jovian radii, and Thebe provides an upper bound, which is 4.06 Jovian radii. So the craters on Amalthea. Yeah. Okay. Great question. So yeah, they're heavily cratered. They don't impact because you can, so they would impact rather if the reaccretion time was slower than the differential precession time. Okay. So imagine you come in, you shoot one of these things, it breaks apart into a bunch of pieces, right? Those pieces are all occupying the same orbit, but those orbits can differentially precess, right? If the differential precession takes them away, then bad. But as it is, the reaccretion is basically instant. Okay, so by measuring the inclinations, right, and matching them to Io's outward migration, you can constrain where Io originated pretty well. I was super happy when I figured this out because I thought it was kind of a big deal. But turns out I was not the first person to figure this out at all. And my undergrad advisor, Greg Laughlin, used to tell me never fully solve a problem. Like if you fully solve a problem, just get the full answer, then you won't get cited ever because there's no one left to work on this problem. So just get like halfway, maybe 70% of the way there, but don't ever fully solve the problem. Okay. So here is an abstract that actually fully solved the problem in 2001 by Doug Hamilton. It was never published as a full paper because the abstract already says everything that needs to be said. Okay. It basically said everything I just told you. And it's got a whopping 3 citations. Okay. Because they fully solved the problem. And, this was kind of a cool discovery. And, by going into the Wayback Machine, which is like the best website ever, you can go and find slides from a talk that Doug Hamilton gave in 2001. And like, there it is, right? This is the inclination history of Amalthea. You can see how its inclination grows in this step-like fashion, very deterministic, as Io migrates out. And the same is true for Thebe, where it grows as kind of a multitude of additional steps. Really cool. Okay, good. So now that we know where Io is, so what? Well, let's go back to this figure where I told you early in the talk that satellites and planets will stop at the inner edge of the disk. And in fact, these types of simulations have been done by everyone and their brother over the last 25 years. And they all conclude that there exists a factor of where you park and where the disk is truncated. And this factor is close to unity, but slightly bigger. It's 1.13. Okay. The basic dynamics, by the way, of what's happening here is once you are close to the inner edge, then you have this trailing arm of the spiral density wake, right? And so this is a density enhancement in the disk. And that's basically always pulling back on the satellite. And so it's sapping angular momentum away from the satellite. So the torque associated with this arm, which is called the Lindblad torque, is causing the satellite to go in. But once you go close to the inner edge, there's also horseshoe dynamics, okay, which is, you can almost see the outlines of the horseshoe dynamics, which is basically just taking gas and throwing it into the void, where it then gets picked up by the magnetic field and accreted. So that process of throwing gas in creates a torque that gives the planet angular momentum, and they cancel out when you park the satellite. I'm sorry, not the planet, the satellite, a factor of 1.12, 1.13 away from the inner edge. Okay. So if you know where Jupiter was, you can then divide that. Oh, shit, not Jupiter. I'm sorry. If you know where Io was, you can divide Io's primordial orbit by 1.13 and understand where the disk was truncated. And 4.04 divided by 1.13 is 3.6. Okay. This is where the Circumjovian Nebula ended, okay, by the process of magnetospheric truncation. Okay. You had a question?
Oh, very cool.
Oh, it's cool. Yeah, well, it's actually pretty hot. Okay, right around next to Jupiter, it was like 1,500 degrees, and I have no artistic skill. Okay, but I did have a grant that I could do whatever I wanted with, so I paid a guy to draw this picture, and this picture basically shows everything I just said. This is where the Circumjovian Nebula is truncated, right? It's truncated by the magnetic fields. You've got some meridional flow. You've got the thermally ionized disk. And a critical consequence of this truncation is that it also tells you how Jupiter was rotating at this time. Because, in fact, all of this business with circumstellar disk truncation came from the realization that, like, T Tauri stars do not spin at breakup, right? They spin at a period of a few days. And that's because they spin at almost co-rotation with the truncation period of the nebula. Let's think about how this works. If you write down the equation for the spin angular momentum evolution of Jupiter, you've got a whole bunch of terms, okay, plus magnetic braking, right? This is just Lorentz torques of the field coupling to the disk, and because the disk is going Keplerian, so slowly compared to, say, the spin of the planet, the field lines sap angular momentum away from the planet. You also have accretion of angular momentum along the magnetic field lines, which is this term. Now, I took some plasma physics classes as a grad student, and my professor used to tell me, In plasma physics, you have equations with lots and lots of terms in them, okay? But never worry, because always, like, 2 of them cancel out and the rest just don't matter. And in fact, that's the case here as well. All of this first line is like a 10 to the minus 4 correction to the balance of these 2 terms, okay? So if you were to solve this, what you would find quickly is that J dot, the spin angular momentum evolution, would go to 0, balanced by Lorentz torques breaking the spin and accretionary torque spinning up the planet. And when you plug in the numbers for a dipole field, what you get is that the equilibrium rotation very quickly, in like 10 to the 3, 10 to the 4 years, approaches 0.88 of the orbital frequency at which the disk is truncated. So if you know the mass of Jupiter, which I do, it's 300 Earth masses, and I know where Jupiter was truncated, it's 3.6 Jupiter radii, I also know the period with which it was spinning at this time, and it turns out to be about a day. Now, then the disk photoevaporates, right? The photoevaporation front comes, reaches Jupiter, and it's gone. What happens after? Well, what happens after is that the spin angular momentum of Jupiter is conserved to a great approximation, because the satellites are actually tiny compared to Jupiter, so their tidal migration extracts a negligible amount of angular momentum. And so, if you know how it was spinning to start with, and you know the angular momentum now, right, and you know the moment of inertia now, and in general, moments of inertia can be computed as a single valued function of the radius with standard, planetary structure evolution calculations like, those you can do with the MESA code. Then you can just plug in the numbers, and it gives you what the radius of Jupiter was when the disk went away. Okay? It turns out to be 2. Okay? Jupiter was twice as big as it is now when the Circumjovian nebula evaporated. This is a highly boring answer, okay? Because before I did the calculation, I guessed what it was, and I guessed 2. Because, people know that like T Tauri stars are 2 times the radius of the sun. And I was like, it's probably 2 Jupiter radii. And this is indeed a literature that people guess, a number that people guess in the literature already. But this is kind of a model-independent way, I would argue, at getting at this. Okay, so what else does this tell you? Well, if you have the radius and you have the mass for a giant planet, that gives you what the interior entropy of the planet was. And the numbers clock in at a little bit higher than 10 kb per baryon. So this corresponds to a pretty hot start of the giant planet, which means that most of the energy of the accretionary infall was not radiated away as a shock. Most of it contributed to the deep interior. Okay. The entropy is a subtle point. It's kind of fun, but let's get back to something Brian said I would tell you, which is the magnetic field. Okay. Remember how early in the talk I said that for all astrophysical, spherical, rapidly spinning dynamos, there exists a scaling law between flux, like luminosity, and the field. You can apply that same scaling law here and deduce that to the extent that that scaling law is correct, the magnetic field of Jupiter when the disk went away was about 200 Gauss. Okay, and that's a factor of like 50 higher than it is today. Okay. And finally, once you have the field, you can go back to the formula of the ram pressure equals magnetic pressure to deduce what the accretion rate through the disk was right as it went away. And that gives you about 1 Jupiter mass per million years. Okay. So, what do we know now? Well, now we know that this quasi-universal 3-day pileup of planets and satellites is a natural consequence of the interplay between disk accretion, Kelvin-Helmholtz contraction, and just dynamo generation in a fully convective object. And in the Jovian system specifically, you can read off what the IO initial starting position was. And from this, you can deduce that Jupiter was twice as big as it is now when the disk went away. It had a field of a couple hundred Gauss and was accreting matter at 1 Jupiter mass per million years. But like, I kept saying that this is at the time when the disk goes away, right? This is at the terminal stage of the Circumjovian nebula. So when is that, right? Is that 1 million years after CAI formation, 5 million years? Like, what's the number? Turns out it's 3.98. And this is a well-known number because of something called angrites, okay? Angrites, I always assumed just stood for angry meteorites. Turns out it's not the case. It's named after some basin in Brazil. But angrites are meteorites that came from a parent body that was volcanic. Okay, and the parent body lived for, something like 12 million years. So you can date them and you can tell each one what time after calcium aluminum inclusion formation each of these meteorites erupted. But because they erupt and then cool down, they go through the Curie temperature, right? So they record the magnetic field that they see. And you can see that at 3.98 million years, the field goes from a couple Gauss to like 0. Okay. And that's interpreted, people in the kind of that paleomag world kind of agree that what's going on is they were interpreting the field of the circumstellar nebula. And then once the nebula is gone, they don't see a field anymore. Okay. So the lifetime of the nebula is in the solar system actually pretty well constrained to about 4 million years after CAI formation. So all of this stuff, the measurement of the entropy, the field, the radius, all of this puts a point on Jupiter's formation at 4 million years after CAI formation. Now, like, is this a complete history of how Jupiter formed? Of course not. But I'm actually working with a student in Switzerland right now who is doing evolutionary calculations, and he's showing that there's actually a lot of information that can be deduced by matching this point and today's state, right? So forward modeling can actually rule out a lot of things. Actually, yeah. So once you let go of the nebula, its Kelvin-Helmholtz contraction time is like 1 million years. So in 1 million years, its radius is now down to 1.5, something like this. Then like that contraction slows down, but it's, instant compared to the age of the solar system, right? It's sort of tens of millions of years.
Well, all this talk about entropy has made me hungry to fill up my... I'm running dangerously low on calories.
Mm-hmm.
The experts say, and you should know this after your harrowing escape from LA, that, they say to have 6 months worth of food, on hand at all times, for emergency. So I keep it on my body. I just keep the food on my body at all times. Calories are there. It's close.
I only have the beer.
Konstantin, I love talking to you. One of the most exciting and interesting minds in this whole field. I'm grateful that you came down. Other than that, we'll be sure to get you back on when we get that 5 sigma becomes 6, 7, 8 sigma, hopefully in the future. And just can't wait to see where these investigations go. I love what you do, and it's so different from what I do that it really is kind of like a hobby that's it's like appreciating fine art. It's like something that another expert does that's just so gratifying to know that there are people like you out there, because I couldn't do what you do, and it's so gratifying.
Right back at you.
All right, my friend. Thank you so much. Let's go grab some lunch at the Factory Hub.